Hi, this video is going to cover Chapter 12 of our Introductory Chemistry class. This chapter is called Liquids, Solids, and Intermolecular Forces. So we're going to start with the liquids and the solids and some properties that we've already talked about, and then going a little bit more in depth on new things. And then the last half is intermolecular forces, and so we'll define those as well as talk about some of the different types. So starting off with looking at our solids, liquids, and gases, and I believe we've looked at all of these before except for that last row on this table. So we have our gases right here, and we know that our gas molecules are far apart. Look at all that empty space, and they're always in motion. And because of those two characteristics, they're going to have a very low density, a shape and a volume that will fill their containers, and our new thing, the reason behind all of this is that they have weak intermolecular forces. Liquids, on the other hand, have molecules that are held together pretty tightly, but notice there's a little bit of space because they can wiggle a little bit. Those are my little wiggle lines there. And because of this, they have a high density because they're packed together really well. That also means that their volume can't change, but because they have a little bit of wiggle room, they can change their shape. And they have a moderate amount of intermolecular forces. I used the term, but just to point out, IMF is an abbreviation for intermolecular forces, and I use that abbreviation on the slides throughout. And then our last one over here are solids. So notice our molecules down here, they're packed together very tightly. There's not a whole lot of movement between them, and there's no empty space. So because of that, they have a high density, their shape and their volume aren't changing, and all of these are due to the fact that they have strong intermolecular forces. We did talk about the two different types of solids. We have our crystalline solids, which have geometric order, lots of patterns. Salt and diamonds fit into this category, so things with flat faces and strong corners and edges. And then the amorphous solids are, I always think of them just a pile of atoms. It's when there's not really any pattern or order to it. It's things that we can kind of heat up and bend and manipulate pretty easily. So plastic and glass fall into this category. So we're going to talk about some of the specific properties that go along with liquids. And one of them is surface tension. Surface tension is the ability to minimize surface area. So this is the reason why you'll see water droplets actually form like a half sphere, like on your windshield or on a leaf. It's also the reason why our little lizard friend up here can run on water. And the reason behind this is intermolecular forces. That's going to be kind of our go-to answer in this chapter. But down here in our model of the surface of the water water molecule that's on the surface up here, these little black dotted lines are representing those intermolecular forces, those attractions, and it's being pulled only in the downward direction and equal to where it's located. Whereas when we look at this molecule that's in the interior, it's being pulled in every direction. So because the molecule that's on the surface doesn't have anything up here to pull on it, it's just being pulled down towards the surface. It almost creates this skin on the surface. So when a chemical has stronger intermolecular forces, it's going to have stronger surface tension. Another property is viscosity, and viscosity is the resistance to flow. So that means that if something is more viscous, we might describe it as being thicker. So there's maple syrup on there. Molasses would definitely fit into this category, or chocolate syrup. So really, if you think of pouring anything slowly, it would fall into this category. And this has a lot of similarities to our last property. The intermolecular forces are kind of holding those molecules together, and so the stronger the forces, the less it's going to be able to flow or pour. So stronger intermolecular forces are the result of a larger viscosity. We've talked about some of our phase changes: boiling, freezing, melting. We're going to talk a little bit more about them today, what's actually happening on the molecular level, and then just a little bit of math in this chapter that goes along with it. And we're starting with evaporation. So we know that boiling is going from a liquid to a gas. Evaporation is also going from a liquid to a gas, but there is a difference between the two. Evaporation is when the molecules that are on the surface get enough energy and can break free and become gas molecules. Going through a phase change, liquid to gas, requires energy. And once they get enough energy from heat, from a transfer of energy from the other molecules, then they're able to escape. We'll talk about boiling in a couple slides, so we'll talk about the difference, but remember that this is surface only. The opposite of this, so going from a gas back into a liquid, is condensation. So once we have those gas molecules, we know that gases are always moving around crazy all the time. If those gas molecules run into the surface of that liquid, they can get turned back into a liquid. We can increase the rate of evaporation with three ways. If we increase the surface area. So think about it this way. If you have a cup of water and you just let it sit on the counter for a week, some of it's going to evaporate over time. But if you take that same cup of water and now you just pour it on the floor, it's going to evaporate a lot faster because there's more surface area. So with evaporation, it's only the molecules that are on the surface that are evaporating. So if there's more surface area, there's more molecules that have the potential to evaporate. If we increase the temperature, we're increasing the rate of evaporation. This one makes sense on, just on a normal level. We know that when things are hotter, they're going to evaporate faster. The reason why is more temperature means more energy. That means we're giving those molecules on the surface more energy to then escape and turn into a gas molecule. And if we have weaker attractive forces, or really that's saying intermolecular forces, then it will evaporate faster. This isn't something we can change for a molecule. This is more of a comparison. So if we were comparing two molecules, we could say one would evaporate faster than the other based off of those intermolecular forces. And then two more words down here. Liquids that evaporate quickly, the label that we give them is that they are volatile, and ones that do not are called non-volatile. So if you've seen those words, sometimes you might see them as a warning, this contains a volatile liquid. Sometimes that could be either if the fumes are hazardous or if the fumes are flammable. And so that's why you're being warned about it being volatile. So being volatile itself is not dangerous, but depending on what those fumes are, the fumes themselves could be dangerous. So back to our evaporation and condensation. If we let this happen inside of a closed container, so the picture here is of our Erlenmeyer flask with a stopper in it, and we have water molecules. And whenever I always talk about this, I always think about the water bottles in your car, because everybody always has at least that one water bottle that's half full on the floor of their car somewhere. But when you have that closed container, in the beginning, we have mostly liquid water, and some of it is starting to evaporate. So we can see some condensation there, but we definitely have some water molecules in the vapor phase. After some more time has passed, we have our gas molecules flying around here. Notice that the arrows are going in both directions, so we have the evaporation and the condensation. And eventually, I'm gonna move my video here. Eventually, we reach dynamic equilibrium. And what that means is that the rate of evaporation and the rate of condensation are equal. So you can think about it that every time one gas molecule evaporates, another one condenses. So they're happening at the same speed. So the overall number of gas molecules and liquid molecules is staying constant, even though the change is still occurring. One more slide within this category is the definition of vapor pressure. So when we have that closed system, we've allowed the solution to reach dynamic equilibrium. We have all these gas molecules up here. The pressure that those gas molecules have is called the vapor pressure. So the vapor pressure is the partial pressure exerted by that evaporated gas. And it's going to depend on the intermolecular forces and the temperature. So if we have stronger intermolecular forces, that means the molecules aren't going to evaporate as easily or as quickly, so we will have less of them and a lower vapor pressure. If we have a higher temperature, that means more molecules are going to be evaporating, and we will have a higher vapor pressure. So switching over to boiling. So this is also going from a liquid to a gas, liquid to gas. The difference between evaporating and boiling is where those molecules are coming from. So evaporation is when the liquid molecules on the surface get enough energy to escape the surface and become a gas molecule. Boiling is when a liquid molecule in the middle of the solution gets enough energy to escape through and become a gas molecule. So it's going to require more energy because it has to break through a lot more of those intermolecular forces. Oh, let's see. I thought there was one more thing on there we needed to talk about. Oh, there is one more thing. The temperature where a solution boils is called the boiling point. So this gets abbreviated as just BP. And this is the temperature when the vapor pressure of the liquid is the same as the atmospheric pressure. So when the vapor pressure is equal to the atmospheric pressure, then our solution will boil. And so this is also why the boiling point of a liquid changes if you are at higher elevations versus lower elevations. So if you ever bought a cake mix and on the side of it, it has different directions for higher elevations, it's because water is boiling at a lower temperature. And so when we bake something, a big part of that is cooking off or evaporating off the moisture. And so it's doing that at a lower temperature, so the baking directions have to be slightly different. So we're coming into the small amount of math that's in this chapter. Evaporation and condensation are opposite processes. Evaporation is liquid to gas, condensation is gas to liquid. Evaporation is endothermic, so that means that heat has to go into the liquid in order for it to go through that process. The example I have on here is rubbing alcohol on your skin. So if you've ever cleaned your skin with rubbing alcohol, or even just using antibacterial gel, you know that it gets cool. And the reason for that is the rubbing alcohol is evaporating, but in order to do that, it's stealing the heat from your skin in order to do that. So as it takes away your heat, your skin is cooling down. Condensation is exothermic, and so that means that when a gas turns back into a liquid, it's going to release heat. So my example here is a steam burn, which I hope you've never had, but steam burns are very dangerous for a couple reasons. One, it's hotter than boiling water, so it's a hotter temperature, but also when that steam hits your skin, it turns back into a liquid. So not only are you getting the heat from the steam itself, but as it condenses, it's releasing its extra energy, its extra heat to go through that condensation process. So steam burns are very dangerous. If anyone's been a barista, you've definitely experienced them. That's what I did in high school. So here's the number side of it. The heat of vaporization, so we abbreviate it with our symbol here, delta H of vaporization. Remember, H stands for enthalpy, which is our energy in the form of heat. This value is the amount of heat needed to vaporize 1 mole of liquid. And down here we can see heat of vaporization. Notice the units are in kilojoules per mole. The condensation is the opposite of this. So the delta H of condensation and the delta H of vaporization are the same number. It requires the same amount of energy, but in the opposite direction. The heat of vaporizations are positive numbers. The heat of condensation are all negative numbers, but the same numbers. So for example, water requires 44 kilojoules per mole in order to vaporize, but if it's condensing, it's going to release 44 kilojoules per mole. So we're going to do a practice one with this math. It's fairly easy. I just want you to see one gone through though. How much heat is needed to vaporize 77 grams of diethyl ether at room temperature? So we know that we have 77 grams of diethyl ether. So I'm going to go back to that table to get some more information. And here's my diethyl ether in that last row. And so I know that the formula is C4H10O. And the other thing that my problem over here tells me is that we want to know how much heat is needed at room temperature, which is an important point because notice there's a heat of vaporization at boiling point and at 25 Celsius. 25 Celsius is room temperature. So the number we want to use here is 27.1 kilojoules per mole. So my delta H of vaporization is 27.1 kilojoules per mole. So we have grams and we have our kilojoules per mole. Because it has 2 units, we can definitely use that as a conversion factor. But that means we need something else. Our units here aren't matching up. So to go from grams to moles, we know that the molar mass can do that for us. So the molar mass, C4H10O, is 60.1 grams per mole. So I just did that ahead of time for us. So I'm going to start with my given 70.0 grams per mole. So I'm using that molar mass to get us into moles. 60.1 grams for every mole. And then according to the table, moles on the bottom, so it cancels out, kilojoules on top, 27.1 kilojoules for every 1 mole is our heat of vaporization. So I put this in my calculator, and my calculator says 34.72. So we do our normal checks, and grams is canceling, moles is canceling, we're left with kilojoules. We go back and look at our given information. That tells me 3 significant figures, so this gets cut to 34.7 kilojoules. There we go. And the number makes sense. We have a little bit more than a mole. A mole weighs 60 and we have 77, so a little bit more than a mole. And we have a little bit more than our given value that we had. So it fits in with our range that we would expect. So we talked a lot about liquid properties. We're going to look a little bit at solids. This is a heat diagram. So on the y-axis over here we have temperature, and on the x-axis we have heat added. So this would be in joules or kilojoules. And the graph almost looks like stairs. So in the first part of the graph down here, we are adding in heat and the temperature is increasing. So it's still in solid form, but we're taking that solid and we're warming it up. Then there's this area of the graph where it's just a flat line. This is when the solid has reached its melting point. So this is a graph for water. So right there we're at 0 degrees Celsius is the temperature that ice melts at. We could also think of it as it's the temperature that liquid freezes at. The melting point and the freezing point are the same, just kind of depends on what direction you're headed. So notice that we're still putting heat into our ice, into our solid, but the temperature isn't increasing. It's a flat line. And this is because that added heat is going into the melting process. If we have a solid and it's stuck together, it maybe can wiggle a little bit. In order to get to a liquid, it has to do this. So that extra heat is helping to break those attractions that are holding it in place in order to get into a liquid. So that heat that's being added is going into the melting process. And then once all of the solid has melted, now over here we are in the liquid phase. And now as we add in heat, we're just making the liquid hotter and hotter. So again, we have two opposite processes. Melting is an endothermic reaction. We have to put heat into it. And when you put heat into it, that means the surrounding area will cool down. So as you put ice in your drink, it's melting and it's causing your drink to cool down. The ice is stealing the warmth from your drink in order to melt, and as the result, your drink cools down. Freezing is an exothermic process. So as something freezes, it has to release that extra energy in the form of heat. This is the reason why you have a fan in your freezer to keep the air circulated, because if you put something in there that's not frozen, as it freezes, it's releasing that extra heat, that extra energy, and the air has to be circulated. We have the same values for freezing and melting as we did for evaporating and condensing. So the value for melting is called the heat of fusion, and the variable for freezing is called the heat of crystallization. I got a little tongue-tied there. The names for these ones aren't as clear or aren't as obvious, but so we have the delta H of fuge and the delta H of crystal, and again they are the same numerical values, but they are opposite signs. So our heat of fusion and our heat of crystallization are going to be same number, opposite signs. And then the last thing down here, it says that the heat of vaporization is larger than the heat of fusion. So if we look at water, the amount of energy it takes to evaporate water is more than the amount of energy it takes to melt water. So for melting water, we're going from a solid to a liquid. So some of those intermolecular forces, some of those attractions have to break. But as we go from a liquid to a gas, all of those intermolecular forces have to break. So we're kind of moving into the other half of the chapter. And the other half of the chapter is the intermolecular forces half. So I've mentioned that phrase quite a few times, and we're going to talk about what they are now. And the intermolecular forces are attractions between two molecules. And they are all electrostatic attractions. So that just means a positive and negative attraction. And so sometimes that can mean between ions. There we go. Between ions, it can mean between the partial positive and partial negative of a polar molecule. It can even happen in molecules that don't have that polar attraction with temporary dipoles, and we'll talk about that in a couple slides. Larger charges have stronger attractions. So I mentioned this in a previous chapter, but if we have a +2 and a -2, those will be a stronger attraction than a +1 and a -1. And we're going to talk about 4 types, and we're actually going to talk about them in order from weakest to strongest. So our dispersion forces are the weakest out of all the ones we're going to talk about. Dispersion forces exist in all molecules. So as we talk about these, we're going to talk about where they exist, what type of attraction it is, like where that positive and negative is coming from, and then what would cause it to be stronger or weaker. So those are really the 3 key things we want to get through with each of these. For this one, I do call them dispersion forces. They are also called, there's another or there because I deleted something. They're also called London forces. The or, I'll fill it in. They're also called induced dipoles. This one actually has a lot of different names, so just something to be aware of. They are in all molecules, like I said. Here's where that positive and negative attraction comes in. Here's our molecule. We're going to start by looking at this molecule right here. And this is a helium atom, and I know it's a helium atom because it has 2 electrons. And so the electrons are moving around randomly, but just by chance, at one moment, both of the electrons end up on the same side of our atom. And that's going to cause a temporary dipole. The partial charges on that atom are going to be temporary because they're going to go away as soon as the electrons move. But before that happens, it's going to induce a dipole, create a dipole on its neighbor. So because those electrons all went to one side, it forced these electrons to the other side, creating this dipole within this atom. And then the same thing happens over here. The electrons move, creating a temporary dipole. Now, with all of these temporary dipoles, we've also created these attractions between the positive and the negative. So that right there is our dispersion force. The attraction between a temporary dipole on one atom and the temporary dipole on the other. So they're instantaneous, they're temporary, but they're real. Now, how this force can vary is that the bigger the atom or the molecule is, the stronger its force. So let me give you an example. Argon atoms versus neon atoms. Argon has a molar mass of about 40 and neon is about 20. Now, the way that we can kind of see these dispersion forces is based off of melting points and boiling points. If something has stronger intermolecular forces, it's going to have a higher boiling point, a higher melting point, it's going to be more viscous, it's going to have a higher surface tension, and it's going to have a lower vapor pressure. So all of those characteristics are a measurement of how much intermolecular forces a molecule or atom has. Argon and neon, here's their boiling points: 87 Kelvin and 27 Kelvin. This one is a higher boiling point, and it's the result of a higher molar mass because it's going to have stronger dispersion forces. All right, let's look at type number 2. Type number 2 is called dipole-dipole attraction, and these are found in polar molecules, and it's the attraction between that partial positive and partial negative ends of our dipole. So here's our molecule. This is a formaldehyde molecule. And in our formaldehyde molecule, it's polar. So this is going back to chapter 10. But we know it's polar because we have a difference in electronegativity. We have an unsymmetrical shape. Oxygen will be the partial negative side of that polar molecule, and the carbon will be the partial positive. So the attraction is between the carbon, or that partial positive, on one molecule, and the oxygen, or that partial negative, on the other molecule. The stronger the dipole, the stronger the attraction. And that stronger dipole is going to be determined by how big the difference in electronegativity is. So here's an example of that. We have a few different molecules on here, and this one is going to be non-polar, polar, polar, and polar. And we can also see that over here. So towards the end of chapter 10, we talked about dipole size and that it can be measured. The larger the dipole size, the more polar it is. So it's actually a measure of what those charges would be. So we can think of it as how strong those partial charges are. So notice that as we go down the line here, it's becoming more polar. And as we go down the line, that boiling point is getting larger and larger and larger. So as our molecules become more polar, their dipole-dipole attraction is increasing, and their boiling points are increasing as well. So we're taking a little bit of a detour before we talk about our last couple. And our detour is to talk about a couple more words that go along with these properties. One of them is miscible. Miscible is when liquids separate, or is when we can put liquids together and they do not separate. So this is based off of polarity. If we have two polar molecules, they will be miscible, or they will dissolve in each other. So the little phrase up here says like dissolves like. That's referred to as the chemist's rule of thumb. So what it really means is that polar molecules dissolve in polar molecules, and nonpolar molecules dissolve in nonpolar molecules. And if a molecule has both parts, it has a polar area and a nonpolar area, then there can be a little bit of a competition. Soap molecules actually fall into this category. So if you try to wash salad dressing off your plate with just water, it doesn't really work. But if you use soap, it does work because the soap's attracted to the polar salad dressing the non-polar salad dressing and the polar water. So it kind of acts as like a middleman. The picture over here is oil and water. So it's actually a homemade lava lamp, which I thought was pretty cool. But oil and water are a very classic example of something that is immiscible, which really is just a fancy way to say that they don't mix. So just to kind of remember those two words, miscible and immiscible, I also just think of them as mixable and immixable, just to kind of remember what they mean. Our third type of intermolecular forces are called hydrogen bonding. And hydrogen bonding are really just a very strong type of dipole-dipole forces, but it's very specific where we find them. We have to have a hydrogen that is bonded to an oxygen, fluorine, or nitrogen. So our molecule has to contain oxygen, nitrogen, or fluorine, and that atom has to have a hydrogen bonded to it. So very, very specific. The reasoning for this is the same as our dipole-dipole forces, but just kind of on the extreme end. So here's our partial positive hydrogen and our partial negative oxygen. That little dotted line right there is representing our hydrogen bonding attraction. And this is an extra strong case because our hydrogen is so small that it can get very close to the oxygen, and our oxygen is also small but also very electronegative, so they can get close together, which allows for that attraction to be even stronger. The term hydrogen bonding is a little misleading. These are not bonds. They're not chemical bonds. It is just an attraction. All the attractions we've talked about so far are temporary. As soon as the molecules move, as soon as they move past each other, that attraction goes away. So these are all temporary attractions. And just a reminder, we are talking about these in order. So our dispersion forces were the weakest, and then dipole-dipole. Hydrogen bonding is third on that list. Couple more pictures for the hydrogen bonding. So we have water. Remember when we have our water, each oxygen has 2 lone pairs, so it can hydrogen bond to 2 hydrogens at a time. That's actually one of the reasons why water is weird. It's the reason why ice expands when it freezes, why water has such a high melting and boiling point, even though it's a very small molecule. Water's weird, and this is the reason why. All right, so we're going to do a quick practice one before we look at our last type. And this says, rank the following molecules from low to high melting point. So in order to do this, we have to decide what type of intermolecular forces they have. In order to do that, we need to know whether or not the molecule is polar. So here's kind of our thought process. We need to know intermolecular forces type, which means we need to know if it's polar or non-polar, and in order to know that, we need to draw a Lewis structure. So I always refer to it as, well, what's the question behind the question? What do you need to know in order to answer this? And that's kind of the thought process with this. So we went through Lewis structures in chapter 10, so I'm going to draw out these Lewis structures pretty quick here. Also, the way that the formulas are drawn is giving us some clues about what these Lewis structures would look like. It's not just a formula, but also I've been doing this 100 years, so I know what these look like. So we have an ether on the far left over here. This is dimethyl ether. Right here. In the center we have ethanol, and then on the far right we have propane. So when we look at these molecules, the next thing we want to decide is if they are polar or non-polar. And my propane one right here, I know it is non-polar. The carbon-hydrogen bonds don't have a big enough difference in electronegativity, and it's completely symmetrical anyways. My ethanol I know is polar because it has an oxygen in it, so it has something in it that's different. And then same thing with my dimethyl ether here. So if I'm going from low to high, I know, I'm just going to give these guys numbers. I know that molecule number 3 will have the lowest melting point. And the reason why I know this is because it's nonpolar. The only intermolecular force that it has are the dispersion forces. And that's the least That's the lowest in strength. So that's going to put it at the low end of the deal. So that means I have two more to decide from. So when I look at both of these, I know they're both going to have dipole-dipole forces. So they're kind of tied in that regards. But then the next highest type is hydrogen bonding. And we need to have a nitrogen, oxygen, or fluorine. They both have an oxygen, but that oxygen has to be bonded to a hydrogen. And that's what we have here. So this one has hydrogen bonding, but this one over here doesn't. This one only has those dipole-dipole forces. So compound number 1 and then compound number 2 is going to have the highest melting point. So when you see this type of question, you need to draw Lewis structures, decide if it's polar or nonpolar, and then use that information to look at intermolecular force types. Dispersion forces are at the bottom of the list. Hydrogen bonds are at the top of the list in terms of strength. All right, our fourth and final intermolecular force are ion dipole forces. Now these ones are different than the other ones because this is an attraction between an ion and a polar molecule. So we have to have two different compounds. And where we see this the most is when we're dissolving an ionic compound in water. So here we have our chloride ion and our sodium cation. And so notice the water molecules surrounding them and how they're pointed at those ions. So our positive cation is pointing towards all of these partial negative oxygens. So these attractions that I'm circling right here, these are all of the ion dipole forces. And then with our chloride anion, it's pointing towards all of those partial positive hydrogens. So these are all of my ion dipole forces for that ion. Those attractions are what allow an ionic compound to dissolve in a polar solution. So here's our little summary table. And this is straight from your book. It is a great table though because it has all four of our force types, their strength in comparison to one another, where we would find them, and then an example of each. So good table, something to use as a reference as you're practicing. Our last section in this chapter is to talk about different types of solids. So earlier on, we divided solids into crystalline and amorphous. There's actually a lot of different types of crystalline solids, so that's what we're going to look at now. The first type are molecular. So these are compounds that are molecules. So that means that they have the covalent bonds. And when we have a solid made up of these molecules, it's held together by intermolecular forces. And the type is going to vary because it's going to depend on what type of molecule it is. But in general, they're going to have low melting points. The second type on that table were ionic crystalline solids. So these are ionic compounds, and they are made up of formula units. So remember that term is kind of the molecule version of an ionic compound. It's really just saying the lowest ratio. And these are going to have much higher melting points than the other one, than our molecular, because ionic bonds are so much stronger than the intermolecular forces. And then the third type on that list were atomic crystalline solids. So these are just individual atoms. So not ionic compounds and not molecular compounds, but just individual atoms. So this is an aluminum can. Those are aluminum molecules, or aluminum atoms, excuse me. And they're held together, and they can be held together by bonds, dispersion forces, or metallic bonds. And so that actually takes us to one more flowchart. So the atomic solids can be broken up into three categories as well. So the first one are atomic solids covalent. And so these are held together by covalent bonds. The example over here is a diamond. So diamonds are just carbons, and every carbon is bonded to 4 other carbons. So one of the really cool things about diamonds is that a diamond is literally one giant molecule. It's one of those things that I always just thought was really amazing and really cool. They do have very hard structures because they are held together by those covalent bonds, and they're going to have very high melting points. A diamond melts at 3,800 degrees Celsius, so very, very high. Non-bonding atomic solids are just held together by dispersion forces. So the example over here is xenon. So this is also where the rest of our noble gases would fit in. And the melting point for xenon, just for comparison purposes, is negative 112 degrees Celsius. So much lower melting point, much lower forces holding them together. And then our last type in this category, and actually our last slide, are metallic solids. And so these are held together by metallic bonds. And so this is metal cations with electrons surrounding them. It's often called a sea of electrons. So we have metal cations with electrons kind of floating around them. It's kind of a weird concept, and it's something you'll talk about a little bit more in general chemistry, but really you don't even get into it too much there because it's so weird. But this is really where our metals fall into place. So again, we have that aluminum example, copper pipes, iron, or any of our metals fall into here. But that is it. That is the end of chapter 12. Thank you very much.